Professor Woei Chet Lim. Professor Lim has deep understanding of the phenomenon called gravitation spike, as he has been dealing with spikes for almost 20 years. So the title of his talk is BKL and spike dynamics near spacelike singularities. So Woei Chet, please begin. You have, let's say, about 60 minutes for your talk, okay?
Yes, thank you. It's my pleasure to give this talk over Zoom to you guys. So we'll be talking about BKL and spike dynamics near spacelike singularities. So we'll begin with the question, how does a general cosmological solution of Einstein field equations behave near a spacelike singularity? So imagine in this picture here, you have the Big Bang singularity and you're this observer and you're going back in time towards the Big Bang singularity. Now, as you approach this spacelike singularity, how does your space-time behave? So the famous BKL conjecture by Belinski-Khalatnikov-Lifshitz, they conjecture that the behavior of space-time near this singularity is, number one, vacuum dominated, assuming that the matter equation of state is soft. So that is, the pressure is less than the density. So vacuum dominated means essentially it behaves like a vacuum model. So matter doesn't matter. And number two, the spatial derivative terms are small compared to time derivative terms. So the space-time is essentially locally spatially homogeneous. And three, the behavior is oscillatory, where you jump between an infinite number of Kasner states. So you have a sequence of Kasner states, and this oscillation becomes quicker and quicker as you approach the singularity. So let me explain some background to set this up to discuss the BKL dynamics, first in spatially homogeneous spacetime. So there are two main building blocks of the BKL dynamics. They are the Kasner saddle states and the Taub transitions. And these can be written down as exact solutions. And Kasner are Bianchi type 1 and Taub are Bianchi type 2. I'll explain these terminologies later. Okay, so these are the two simplest vacuum and isotropic spatially homogeneous solutions of the Einstein field equations. To describe their behavior, I'll explain this with formulation of the Einstein field equations as a system of first-order ODEs and use the language of dynamical systems. I'll be talking using the terms like state space, equilibrium points, orbits, and attractor. The evolution of a solution is represented by an orbit in the state space. The majority of these orbits approach a special subset called the attractor. Self-similar solutions, these are solutions with a time-like homothetic Killing vector fields. They can be represented as equilibrium points or fixed points in the state space if you use the right choice of state space variables. And how do we choose the state space variables? We use the so-called Hubble-normalised scale invariant variables of the orthonormal frame formalism developed by Ehlers, Ellis, McCallum, Van Els, and Ugla. So it starts with a time-like congruence for the space-time for the cosmology. So you choose your preferred worldlines. You look at its covariant derivative and decompose it into irreducible parts. And you get this symmetric tensor, which is also traceless. This is called the rate of shear tensor. It describes how the universe expands in an anisotropic way. Omega is the vorticity tensor. It is antisymmetric, and theta is the rate of expansion scalar, and u dot the acceleration vector. In cosmology, in astrophysics, most people use the Hubble scalar h, which is 1/3 times theta. And we usually we choose u with 0 vorticity, so we don't deal with vorticity tensor. And then we construct an orthonormal frame. So it's 4 basis factors with E0 equal u and 3 spatial frame vectors, E1, E2, E3. And they are related, this E0 and E alpha are related to the coordinate basis factors, di and di xi, through this relation. These coefficients are the lapse function and the frame variables E alpha I. And we assume orthonormal basis factors. So these frame variables, they combine with this Gij metric. Gij is the spatial part of the metric, and it gives you the Kronecker delta. And E alpha I has inverse this way, E alpha I, and they're related to the metric or line element in this way. So this is Gij. If you can compute Gij from this inverse E alpha I. To further reduce the degrees of freedom, we can align these orthonormal frame vectors to the coordinate basis factors as much as possible. For example, later for Gaudi spacetimes, we align E2 with the y direction and E3 as a linear combination of y and z directions. The orthonormal frame vectors fields they are linear combinations of these partial differential operators with non-constant coefficients. And as a result, they do not commute. And so the right-hand side are non-trivial. They're not zero, and they can be, again, broken down to irreducible parts. And the first line here, you've seen the u dot and h and sigma before. What's new is this capital omega, which is the angular velocity of the spatial frame. And also the second line introduces further variables a and n. And a and n essentially determine the curvature of the spacelike hypersurface, t equal constant.
May I have a question?
Yep.
On the previous slides, you wrote the generic line element in terms of the lapse and then a S3 metric.
Yeah.
Do you know what is the restriction related to this assumption? Or, I mean, is it always true for arbitrary space-time, or?
Well, we are making the assumption of zero vorticity. So we're zero shift. So yeah, so we are choosing zero shift. So there is no the dt, dx components.
No, I understand, but are you excluding spacetimes from the outset, or this is satisfied in general? I mean, this is appears to be a strong assumption. Yeah, this.
Yeah, I understand. But yeah, I don't know the answer to that, whether this is done generally or this is a strong assumption.
Actually, this can be shown to be true for globally hyperbolic spacetimes, but the question is how you choose your physical interpretation. I mean, if you are happy with the globally hyperbolic spacetimes, I can give you references when this is proven to be.
Okay, yeah, so I appreciate that, yeah. So you're saying that if you have globally hyperbolic spacetime, this can be done in general?
Yeah, I think in 2015, Sanchez and Mueller showed something very important about this, but yeah, I will contact you later.
Okay, thank you. Okay, so these commutator coefficients are essentially, you can write them down as partial derivatives of the labs and the frame variables, E alpha I, or the metric. And continuing with this, we want to normalize these variables by dividing them by this Hubble scalar H. So for example, the labs, you can normalize it. So 1 over n is normalized by dividing by h, and I put the new notation, the new variable, the normalized variables with a superscript capital H to emphasize that they are Hubble normalized. Okay, generally we use capital letter for the Hubble normalized variables. And these Hubble normalized variables have the nice property of being constant for self-similar solutions. A self-similar solution is a scale version of itself at any time. An example would be the flat FRW solution. It's a self-similar solution because it has a time-like homotheity factor. Gauge choice, we can use the gauge choice to choose, for example, the Hubble normalized labs to be 1, and this simplifies the acceleration. The u dot is 0, and for the spatial orthonormal alignment, in the example I mentioned earlier, that fixes this spatial frame rotation omega or capital R to be equal to these shear components. And furthermore, the Hubble normalized frame coefficients decouple from the system of ordinary differential equations that describe the spatially homogeneous models. Hubble scalar also decouples. So the reduced state space variables, that is not counting these E alpha I and H, we only have the sigmas, the A, and the N's. This means that the self-similar solutions are represented by equilibrium points or fixed points in the reduced state space of Hubble normalized variables. Spatially homogeneous solutions. Here, these are models with at least 3 space-like King vector fields acting on 3-dimensional manifolds. As a result, the state space variables are functions of time only. And these spatially homogeneous solutions are very important in describing these asymptotically local dynamics of BKL conjecture. So here we focus on what we call Bianchi models. So models with 3 Killing vectors are classified depending on how the Killing vectors interact with each other, whether they commute or they give another Killing vector. And this can be described by whether A alpha is 0 or non-zero, so class A, class B, or you look at the eigenvalues of the n, whether they are 0 or they have the same sign or opposite signs. And you have these Bianchi types from 1 to 9. So the simplest types are the Bianchi 1 and Bianchi 2. The eigenvalues are 0, or you have 1 non-zero eigenvalue. So let's look at the Kasner solution represented in these Hubble-normalized variables, the shear variables are diagonal. You can represent it like this with diagonal shear. And they are also constant, and they lie in a unit circle, sigma plus squared plus sigma minus squared equal 1. And all the other Hubble-normalized variables are 0 because the A alpha is 0 and the n also are 0. So in this Hubble-normalized state space, the Kasner solution is represented by a fixed point on the unit circle. A different point on the unit circle is possibly a different Kasner solution, but there are multiple representations actually. What about the second building block, the Taub solution? They have non-zero n, only one component, and they lie on this ellipsoid. And they are not fixed point, but they are, and the orbit connects 2 Kasner fixed points. Okay, it goes from one Kasner fixed point to another Kasner fixed point. And of course, you can orient them with either non-zero and 2,2 or non-zero and 3,3. So if you draw them and project these orbits, which lies on the ellipsoid, and project it down onto the sigma plus, sigma minus plane, they actually show straight lines like this. So this is for n11 non-zero, the middle one for n22 non-zero, and the right one is for n33 non-zero. And this green triangle is for you to trace this. You can draw the straight lines by connecting this corner. So you just imagine you draw a straight line from this corner across like that. You get these straight lines. So these Taub solutions represent a transition between one Kasner point and another Kasner point. So this gives you a building block for the oscillation between Kasner points. If you look at, for example, Bianchi VIII and Bianchi IX, the n alpha beta has 3 non-zero eigenvalues. Okay. Also, the eigenvectors do not rotate. Having these 3 non-zero eigenvalues, you can have non-stop, non-terminating Kasner oscillation. This oscillations between Kasner points. So essentially, these orbits are built from connecting all these different Taub orbits. So I colored them in 3 different colors: the green one, the blue ones, and the red ones. If you're near a fixed point, dynamically you spend a long time near a fixed point. But this transition actually happens very quickly. You spend very short time doing the transition, but very long time near a fixed point. And this long time near a fixed point is called a Kasner epoch. And if you have a sequence of this alternating color, say between blue and green, you could call this this collection of the blue and green transitions a Kasner era. And once you switch to a different color, then you start a different Kasner era. You go to the next Kasner era. BKL introduced an index U that characterize a Kasner solution that is independent of the spatial frame rotation. And it can be defined implicitly through the determinant of the shear sigma alpha beta, like this. And the BKL index satisfies U greater or equal to 1. And the Kasner map for each top transition can be described as this value of U goes down by 1 for each Kasner, for each top transition, for each jump. That's if U is greater or equal to 2. And the Kasner era ends when U falls below 2. And to start the next Kasner era, you change U to 1 over U minus 1. So you start with a big number again. And there are two interesting Bianchi types, 6 and 7. They can only sustain the BKL oscillation for a single Kasner era because they have only 2 non-zero eigenvalues for n, and even though their eigenvectors rotates they only rotate on one axis every Kasner epoch. And the spatial frame has to rotate with the eigenvectors, so the Kasner points remain on this unit circle on the plane. So this introduces frame rotation, which we call frame transition here. So let me show you the Taub transition orbits. So this is how they look if you draw them in 3D. With frame rotation, we have a sigma cross acting as a variable that describes frame rotation. So we have now an extra transition like this, which are parallel lines. They take you from one representation. It's really the same Kasner point, this point and that point, but different orientation. So represented in this way, the Bianchi VI orbit during a Kasner era goes like this, and eventually it stops at a Kasner point. There's one exceptional Bianchi type, which is called the exceptional. The star means it's exceptional. There's also a non-exceptional one without the star, but here we're interested in the exceptional one, and it can sustain the BKL oscillation indefinitely because even though the n alpha beta has 2 non-zero eigenvalues, their eigenvectors rotate on 2 axes, and having this extra axis of rotation allows it to sustain the BKL oscillation indefinitely. So even though for this case you have 2 frame transitions, and even though the details are different, essentially it's still U going to U minus 1 for the Kasner map. So this is how it looks for the exceptional Bianchi 6 minus 1, 9. This is the Taub orbit. This is the first frame transition with sigma cross. And this is another frame transition with another off-diagonal shear. So they look like this if you project it down to the sigma plus, sigma minus plane. And you can combine these orbits to sustain non-stop BKL oscillation. Okay, so now we're ready to talk about BKL dynamics in spatially inhomogeneous models. And the class of models we consider here are the so-called orthogonally transitive, or OT, G2 spacetimes. These are vacuum models. They have two commuting or abelian Killing vector fields, spacelike, and the group action is orthogonally transitive. And some people also call this Gaudi models. Gaudi models have additional assumptions on the global structure, say the spatial periodicity and so on. And this model contains the Bianchi VI as a spatially homogeneous special case. And this class can only sustain the BKL dynamics for only one Kasner era. But the surprise here is we get spikes. So spikes are small-scale spatial structures that form and then either remain there. In this case, we call them permanent spikes, or they can disappear. And in this case, we call them transient spikes. Permanent spikes were discovered incidentally in numerical simulations of Gaudi models by Beverly Berger and Vince Moncrief in 1993. Their original goal was to understand the nature of the generic singularities, but they didn't expect to find spikes. And this is a good surprise. So what they see is they see this isolated worldlines along which the BKL index U eventually tends to a number greater than 2, whereas others, more typical worldlines tend to value less than 2. So in the end, you get a permanent spike in this OTG2 models. In other words, the spacetime has a pointwise discontinuous limit. Okay, it doesn't approach that limit uniformly. And furthermore, in later studies, numerical simulations, people see that even before this final approach, before you get the permanent spike, you get transient recurring spikes at the same point, at the same spatial worldline. They form and then they smooth out after 2 Kasner epochs, and then they form again at the next Kasner epoch. What is so special about these worldlines where the spikes happen? There are 2 possible explanations. One is the active eigenvalue of n changes sign there. That is, the active eigenvalue is 0 at the worldline where you see the spike. Second explanation is that the trace of n changes sign there. I'm not sure which one is more accurate, so that still needs more research. From a dynamical point of view, the Kasner fixed points are unstable because they are saddle points in the state space. When you have a saddle point, you have orbits that tends to the saddle point, and also you have orbits that comes out from the saddle point. Right? The blue one are called stable manifold of the saddle point, and this black one are the unstable manifold. If you have an initial condition here, you follow the blue line closely. You get close to the saddle point, so you actually slow down here, and then you start leaving and you speed up again like this. But in an inhomogeneous model, you're able to specify your initial data that depends on spatial coordinates. So you could have your initial data that actually spread out across this stable manifold, across this blue line. Okay, and for the initial data that's exactly on the blue line, it will go towards the saddle point and never leaves, whereas other points will leave eventually. So this initial data gets stretched like this at later time, and this is causing very steep gradient. Okay, we see spiky structure because of this. Okay, so this is what I just said. So you could get a spike or maybe a step, like a jump like this, depending on how your orbit behaves. Now, so the argument just now is true if your model is close to spatially homogeneous. That is, if your spatial derivative terms are not too big. If we go to the general G2 spacetime, so if we relax the OT action, then we get an additional shear component that is non-zero, and it gives us enough degree of freedom to rotate the eigenvectors of the n and sustain an infinite sequence, just like the exceptional Bianchi VI minus 19. And when you have this sufficient freedom, you get always transient spike, because it doesn't get stuck. So you don't have the permanent spike anymore. And the permanent spike in the OTG2 is actually a result of the unfinished spike transition, because it lacks the crucial second degree of freedom in the rotation of the eigenvectors. And these spikes have steep spatial gradient, so obviously the BKL conjecture number 2, that the spatial derivative terms are small, is not true near spikes. Okay, so that needs to be relaxed. And luckily, we are able to describe this spike dynamics by exact solutions. And this was discovered in 2 stages. First, in 2008, I discovered the OT G2 spike solution. And this is found by applying solution generating transformation by Randall and Weaver, applied to a Kasner seed solution. And in the second stage, I discovered the non-OT G2 spike, which is always transient, using the Garrosh transformation, again using Kasner as the seed solution. And we were able to confirm numerically that the OT spike solution does describe the numerical simulation of this OTG2 models. So this is done with Anderson, Garfinkel, and Pretorius. And for non-OTG2 spike, the work is still under progress, because there's problem with the numerical zooming technique. So these are the OT G2 spike orbits. There's a parameter that specify where you start on the Kasner circle. So for W less than 1, you end up with a permanent spike where this red orbit and the blue orbit don't meet up. The others, they all meet up. And the pink one are intermediate world lines. Okay, the red one is the spike world line. It's quite different from the typical world line. So the blue one is what you typically see in Bianchi models, right? Just the Taub transitions and the frame transitions. But the red one is the spike orbit. If you're sitting at the spike, you go like this. So for transient spike, they all meet up in the end. That means the spike disappears. But it will start again down here in the next Kasner epoch. So this is a snapshot. So it goes first like this. The blue one, the typical one, goes first. And then the spike orbit will actually complete the transition first, and then the typical ones catch up. For non-OT G2 spike, so typically, if you are with OT, this is the end. You get a permanent spike like this. But for non-OT, it keeps going. It takes you over here and then continues. The red one already completes its transition, and then lastly, the blue one catches up. So they all meet up at the end, so it's a transient spike. So let me talk about the numerical work in 2009. So with spikes, because they get very narrow after each recursion, we need a new algorithm to simulate the G2 models. And the way to do this is to not simulate traditionally like this, even with traditional method where you try to add more grid points to refine your numerical resolution is never enough. The smart way is to only simulate this region here. That is, you try to zoom in only on the neighborhood of the spike. And the boundary comes in either faster than light or at the speed of light, so that you don't have to deal with boundary conditions. This way, you don't need to rely on mesh refinement. And here are the simulations. We have some initial conditions, and we follow 2 generations. So 2 spike transitions. There's one here at some early time and a second one at later time. What's being plotted here are the 4 Weyl scalars. So C is the Weyl tensor, and you can contract 2 or 3 Weyl tensors in different ways to form scalars. So this gives you a space-time invariance, and we normalize them by h so that we normalize the divergence, the blow up, because this unnormalized one blow up to infinity at the singularity. So this time t is increasing towards the singularity. So you can see near we put the spike at x equals 0. So there's a spike, and then there again. And they are transient, so that you see they form and then they are gone. And if you're further away, it's essentially spatially homogeneous. There's no spatial, very little spatial variation out here. And on the left column, here we focus on the first transition. This is the numerical simulation. And here is the matching exact solution. And we are able to match it fairly well to 1 part in 100. And even the large error are closer to the edge, that is further away from the spike. Near the spike is very good. For the second spike transition at a later time, the match is even better. This is almost like 1 part in 10 to the 10. Okay, you can see some error here, but this is really very small error. So the matching is exceptionally good. I think maybe because of the whatever deviation in the initial data is radiated away at later time. So it gets better and better. It converges to the exact spike solution. So these spike transitions are really described by the exact spike solution. Okay, so to summarize, the original BKL conjecture is this. However, the second part here where it says the spatial derivatives are small needs to be modified to account for transient spikes. It is still mostly true in that you don't get spikes everywhere. You only get them here and there. So the transitions that connect the Kasner states are mostly still the Taub solution, but you can get spikes, and these are described by the spike solutions. And we have developed new numerical algorithm with zooming technique to simulate spike transitions. Although for non-OTG2, that work is still ongoing. The discovery of spike solution leads to other research. We also found exact spike solutions with electromagnetic field, and we also look at how spikes interact with matter. And we also found spikes in G1, so only models with only one Killing vector, which means you can have two spikes crossing each other. And we also found spikes that form around an axis. So this is with cylindrical symmetry. This is the latest work. Well, for people studying quantization, because near spacelike singularity, the space-time reaches the quantum regime. So you might want to quantize the space-time there. And what do you see typically? The most common state you see there is the Kasner saddle state. The next most common is the Taub transition. Spike transitions are rare for the transient OTG2 type. And even rarer are the non-OTG2 spike transitions, which are inter-Kasner era. So it's a challenge to try to come up with quantization of these solutions. That's all. I'm at the last slide. Any questions?
So, okay, thank you very much for your clear and interesting talk. And now we have time for questions. Okay.
Or maybe me.
Okay.
I have such a question. wants to quantize gravitation. Thinking in this way, Einstein's equations should be a kind of approximation only of known quantum equations for gravitation. In such case, we rather should think about inhomogeneities as quantum fluctuations, not as spikes, which can be something artificial in this case. What do you think about this?
Well, I'm not an expert in this approach, so I don't have a good comment on whether this is a good idea or a bad idea.
No, it's completely different view on this problem. Okay, thanks. I haven't expected an answer, final answer, but I don't know if anybody tried to do it in this way. Okay,
Yeah, I don't know.
Okay, thanks.
Okay, further questions, please? Comments, remarks?
What is the Taub solution here?
It's the, well, I don't have the exact solution written down here, but it's the vacuum Bianchi type 2 solution. And this is found by Taub in 1963. But if you look at my spike papers, they are written there.
I see. So is it the same solution, which is also called Taub knot?
No, that's a different solution found by Taub with two other people. So he found quite a number of exact solutions.
Right.
Okay, further comments, remarks, questions? I can't hear any, so let me have a question. Okay, so is the sequence of Kasner saddle states connected by spikes transitions generic?
Yes, so there are numerical confirmations in simulations of general spacetime without any symmetry by Garfinkel. So he has done some simulations and showed that this is generally what happens near singularity. It's just a sequence of Kasner saddle states connected by Taub transitions almost everywhere except points where you have spikes.
I see. So this is something missing in the BKL scenario.
Yeah, so BKL scenario is generally true except where spike happens. Then the spatial derivatives are quite large there, so it's not quite true. That second conjecture there.
Yeah, but if the spikes are generic, so you can't, you have to deal with them. You should take into account them.
Yeah.
I see. Okay. Any other questions? If not, many thanks again, Woei Chet, for a great talk.
My pleasure.